resonance and formal charge. So some molecules have more than one valid Lewis structure. So let's look at O3. Anybody know what the name of O3 is? Ozone. So let's see what we can come up with for ozone. Well, we've got 3 oxygen atoms. So they're going to have to be connected. We're not going to make a triangle out of them, okay? This is general chemistry. We are going to avoid cyclic compounds. There are many cyclic compounds. What am I talking about? Doing something like this, where they're making ring around the rosy, okay? That happens a ton in organic chemistry, but this is not organic chemistry. We're going to do some Lewis structures for some organic compounds, but we're not going to make circles, okay? We're not going to do that. So don't do that. Plenty of time to worry about that when you take organic. So here we have 3 oxygen atoms in a row, and each oxygen atom has 6 valence electrons. So we've got 18 dots to deal with, 18 electrons. So I've got 2 here, and I've got 2 here. So 2, 4, 6, 8, 10, 12, 14, 16, 18. I used up all my cookies. I used up all my electrons. Is everybody happy? No. Well, what can we do to make everybody happy? Well, we'll take from the rich and give to the poor. So we'll take one here and have that shared. Okay? Works great with electrons, not so good with money. So this oxygen has 2, 4, 6, 8. This oxygen, 2, 4, 6, 8. This oxygen has 2, 4, 6, 8. Is there another way we could draw that, though? Yeah. What if we put the double bond between these 2 oxygens? That's different because we have 3 oxygens, and yes, they're all atoms of the same element, but they are 3 distinct atoms. So oxygen, double bond, oxygen, single bond, oxygen. Which one is correct? Both and neither. Isn't that a great answer? They're both correct, and yet neither one is correct.
Must be Schrodinger's cat.
Yeah, Schrodinger's cat come back to pee in our dryer. The cat peed in the dryer again last night. It was lovely. The cat has a death wish. In nature, what happens is the molecule exists as an average of the 2 Lewis structures. This molecule would have a dipole moment, not based on its differences in electronegativity, but there's an asymmetrical distribution of electrons. Okay, there's more electrons at this end than at this end, and so we would expect this to be a little bit polar, and we could check that by its behavior in an electric field. But ozone is not polar at all. It doesn't have a dipole moment. It does not line up with an electric field. And due to that and other studies, we understand that actually the bond between these 2 oxygens and these 2 oxygens are actually identical. And they're between a single and a double bond, both in strength and in length. So you could kind of think of them as a 1.5 bond. You're like, how do you do that? Well, Lewis structures don't give us a great way for describing that or for showing that. And so what we do is we show both of the structures, and we put a double-headed arrow, not that fat, a double-headed arrow in between. And we call those resonance structures. Resonance implies kind of bouncing back and forth, right? And so for Lewis structures, we look at it's this and it's that, and it's going back and forth, and then it's going back and forth so fast that it's actually in between. What's really going on is that the electrons are delocalized and they're spread out uniformly all over the molecule. But this is easier to think of as them going back and forth. So you're welcome to think of them as going back and forth as long as you recognize they're not actually doing that. They're in between. Any questions? So the actual structure is called a resonance hybrid. And it's a little bit like if you took one of these. This is a German Shepherd, and that looks like a golden lab. And if you breed these two, what do you end up with? You end up with something that's in between, right? Dog breeders do that all the time. You can get a cockapoo and all these different combinations. Some of them are really neat. This dog is a hybrid. It's part this and part that. But it's not going back and forth. It's not like one day it's a German Shepherd and the next day it's a lab. It's not going back and forth. It's always the same, and it's a combination of the two. And so what we have for ozone is it's a hybrid of these two Lewis structures, and it actually looks more like this. We call it a resonance hybrid structure, and it's difficult to draw using Lewis structures. But the electrons are localized in the Lewis model, meaning we have to choose this second bond here, this double bond, the second pair of electrons. It has to be either between these two atoms, or between these two. It's localized. But in nature, it's actually delocalized, and they're spread out over the whole molecule, or at least several atoms or bonds. And this results in a lowering of the energy. Lowering of energy is good. It's stable. You think, something that's very, very tall has higher potential energy, right? Because when it tips over and falls, it's got farther to fall. And if you get lower to the ground, you're more stable, right? You have lowered your potential energy, and that's a more stable situation. So we call this resonance stabilization. So you need to recognize when you have a possibility for resonance, and then when you're drawing a Lewis structure, you need to write the different ones. So let's do this. What's the name of this ion? Nitrite. Okay, I know we tested on that, but the class isn't over, so we can't forget all those. So we're going to do a Lewis structure for nitrite. So we have three atoms here. We have to decide how we're going to stick them together. Should we do this, or should we do this, which looks like, oh no. The second one, we had a guideline that said hydrogen atoms are terminal and generally put the more electronegative element terminal, meaning on the outside. So if we look at nitrogen and oxygen, oxygen is closer to fluorine. Oxygen is more electronegative. So we're going to put the nitrogen in the middle and the oxygens next to it. So we'll erase that one. And the next thing we need to do is figure out how many electrons are we dealing with. Well, we have 2 oxygens, and each of them has 6 valence electrons. And then we have nitrogen with 5, and the negative sign tells us we need to add 1. So we've got 18. So here we've already put in 2, 4, 6, 8, 10, 12, 14, 16, 18. Just my style of drawing Lewis structures, I just start somewhere and I just kind of try to spread them out as much as I can till I run out. I ran out. Is everybody happy? No. This oxygen isn't happy. This guy's happy. So what we need to do is we need to have him share one of his lone pairs with the oxygen. So I'm going to take this lone pair off and have that nitrogen share with the oxygen. Now everybody's got an octet. Everybody's happy. And then we need to put brackets around this because it's an ion and put a charge on the outside. When you're looking for a resonance structure, it generally involves double or triple bonds and between the same kinds of elements. So if we look here we've got nitrogen and it's bonded to two oxygen. One gets the double bond. Why that one? Why not this one? Well, this one should have a double bond in the other structure. So we have nitrogen bonded to two oxygens, and we're deciding where do we put the double bond. We have two equivalent places. That means there's going to be resonance structures. So I'm going to draw this down below because I didn't leave room to the side. I'm going to put a double-headed arrow between them. So that tells us that in this molecule, this double bond is actually delocalized over both of these bonds. And so each of those is really a 1.5, and we have a resonance hybrid that is between these two. Any questions? Some molecules and ions have more than 2 resonance structures. Some have 3 or 4. Formal charge. So this is where we get more specific about where we should put the electrons and how we should bond everything together. So formal charge, the formal charge in a Lewis structure is the charge it would have if all the bonding electrons were shared equally between the bonded atoms. This is a fictitious thing. This is something we made up to help us figure out how to draw the Lewis structure that matches up with what we observe in nature. These are not charges. This is something made up. It's a little bit like oxidation states or oxidation numbers. That was also kind of a made-up thing. It just helped us keep track. But it's not quite the same as oxidation numbers. And so we calculate this by ignoring electronegativity. We're going to ignore the electronegativity. And basically what we're looking at is the difference between the number of valence electrons and the number of electrons that it owns in the Lewis structure. So the formal charge is the number of valence electrons that that atom had before it came into the compound. How many cookies did that kid bring? Now we care. And then, this is a confusing way of writing out how many does it own. It owns all of its non-bonding electrons and half the bonding. And you subtract those, and that's more confusing than helpful. So hopefully we'll clear that up doing some examples. So, rules for these formal charges. The sum of all formal charges in a neutral molecule must be 0. The sum of formal charges in an ion must equal the charge of the ion. And what we're looking for is a Lewis structure that will give us small or 0 formal charges on individual atoms. So, like I showed you, there's sometimes different skeleton structures that you can make. And how do you choose? Well, this is a more concrete way of how do you choose. So you can look at both of them, calculate the formal charges in all the atoms. The one that has the smaller formal charges, or preferably even 0, is going to be better. When you can't avoid formal charges, now we're going to look and see who's the most electronegative atom. Then if you have negative formal charges, you want to put that on the electronegative atom. Because what a negative formal charge means is that that atom is getting more than its share of electrons. And the electronegative atom is the one that's going to do that because it's more attractive to the electrons. So looking at hydrogen cyanide, there's two structures here. They're kind of hidden in here. One structure is this: hydrogen bonded to carbon with a triple bond to nitrogen, and nitrogen with one lone pair. Or we could stick the nitrogen in the middle and put the carbon on the outside. Those are really the only two choices we have in drawing this Lewis structure. How do we know which one is better? Well, one way is to look at electronegativities, and we would say nitrogen's more electronegative, that one should be terminal. And for this example, that works. Some examples are more complicated, and that's not going to solve the whole problem. So let's see how the formal charge idea works here. So we're going to look at the number of valence electrons. Hydrogen has 1 valence electron, carbon has 4, nitrogen has 5. Now what I'm going to do is I'm going to look at the electrons that the hydrogen owns in this structure. I'm going to draw this out bigger because that's kind of hard to see. So here we've got H, we've got C bonded over here, and he's got this guy. So I'm going to draw a line here. We know that these guys are not sharing equally, but for looking at formal charges, we're going to assume they're sharing equally. And so all the bonds get split, and hydrogen only gets to count his half of the bond. So hydrogen in this Lewis structure owns 1 electron. Does that make sense? There's a double bond, you get to share, you get half of what you're sharing. And then we look at carbon. Carbon's got half of this bond and half of each of these bonds. So 1, 2, 3, 4. So let's put that might help. Right? Because the double bonds, each bond is 2 electrons. So carbon owns 1, 2, 3, 4. And nitrogen owns 1, 2, 3, 4, 5. Okay? So if we take the number, let's write it down here. So this one's got 1 and 4 and 5. Now they're doing that whole number of non-bonding and half the bonding. If you like that, you'll understand the table, and I'm not going to mess with it. I'm guessing most of you are not going to like all of that, and so this is how I think about it. I just look at the diagram and I say, well, what is carbon? What could he call absolutely his own? Well, he could count 4. How many did he bring in? He brought in 4. 4 minus 4 is 0. He has a formal charge of 0. Hydrogen brought in 1 electron. Hydrogen as an atom has 1 valence electron. In this molecule, hydrogen could say, I own this. Carbon's sharing this one with me, I'm sharing this one with carbon, but this is mine. So hydrogen has 1. 1 minus 1 is 0. Nitrogen owns 5 electrons. It came in with 5. 5 minus 5 is 0. Does that make any sense? Yeah? Okay. So let's look at this other structure in the same way. Hydrogen bonded to nitrogen with a triple bond to carbon and a lone pair over there. And again, I'm going to put these dots in here just to make it more obvious that those are electrons there. And then I'm just basically going to cut these in half. These just weird analogies come to me. So remember I talked about how, this would be me and my husband and we share 6 children between us. We're not getting a divorce, but this would be like carbon and nitrogen getting divorced and everything's going to be split equally. You get half the kids and the other person gets half the kids. So that's what's going on here. So here, hydrogen is going to end up with 1 kid, 1 electron. Nitrogen is going to end up with 4 and carbon's going to get 5 because these were on the outside. So half of the bonding electrons and then any of the lone pairs. So do you see how I came up with those numbers down there? Nod your head. or shaken. I then compare this number to the number of valence electrons that carbon has. Carbon has 4 valence electrons. In here, it's got 5. 4 minus 5 is -1. That means the formal charge on carbon in this Lewis structure is -1. So there's its formal charge. Nitrogen owns 4 electrons in the Lewis structure. It came in with 5. 5 minus 4 is +1. Hydrogen owns 1. It came in with 1. 1 minus 1 is 0. So in this structure B, we have formal charges on our nitrogen and carbon. Nitrogen has a +1 formal charge. Carbon has a -1 formal charge. Now, is that horrible? No. But then we look and see, well, is there another way we can draw this where the formal charges are lower or 0? And yes, there is. This one had all 0 formal charges. 0, 0, 0. That's better. That's more stable energetically. And this is how the molecule is in actuality. It does not form this molecule. That's not how it connects. So formal charges are just a device that help us predict what nature does. Any questions? I can just tell you're going to love this, right? This is going to be so fun. Great, another stupid game for us to learn how to play. So let's assign formal charges to each atom in the resonance forms of N2O. Which resonance form is likely to contribute most to the correct structure of N2O? Well, let's draw a structure for N2O. Well, how about let's try something symmetrical? We could try nitrogen, oxygen, nitrogen, and see what we get. How else could we connect those? We could put the 2 nitrogens together, right? How do we choose? Well, the rule of putting the more electronegative element on the outside might suggest that this is the correct one, but it's kind of iffy because that's not very symmetrical, and usually things are more symmetrical like that. So this is where formal charges really help. So let's finish out these Lewis structures. We have 2 nitrogens and 1 oxygen. So 14 and 6, we have 20 electrons. So we're gonna throw those around. Here we've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Well, there's no double bonds, are there? But I thought you said resonance structures usually involve double bonds. Well, usually, not this time. So there's a Lewis structure. Is everybody happy? Question.
Nitrogen 5%.
Thank you. Okay. Thank you. Wait, that's not what I meant to do. Okay. Thank you. Yes. I had a brain fart. Nitrogen has 7 electrons, but only has 5 valence electrons. I thought that was not looking very good there. Okay, let's just rewind. Okay, nitrogen has 5, and then 6, so 16 electrons. Is that better? Yeah, thank you. I am not always correct. I'd like to think so, but not. 2, 4, 6, 8, 10, 12, 14, 16. We're short electrons, because this time I counted correctly. So we need to move some from non-bonding pairs to becoming bonding pairs. So how about we take one from this oxygen and put it over here. So we'll take this pair out and put it in here. We have not changed the number of valence electrons in our structure. Is everybody happy there? No. Well, we could take another pair of electrons from the nitrogen and put them over here. Does that work? It works. What if instead of having a single bond over here, a double bond on each side, what if we had a triple bond on one side and a single bond on the other? Could we draw that and make everybody happy? We could. So let's do it. You're thinking, let's not, and say we did. Do people still say that? That was a big thing when I was a kid. So going from here to here, what I did is I took this lone pair and I gave it to that nitrogen, and I moved this double bond over here, and I've still got the same number of electrons and still got everybody happy. And the difference between those two is just the position of a multiple bond. And what about this lonely guy over here? Well, let's see how he works out. Again, 16 electrons, 2, 4, 6, 8, 10, 12, 14, 16. There's no surprise, we're going to need some double bonds. So let's take these guys out and make a double bond over here. That's not quite good enough. So we'll take this one out and make a double bond over here. Now these two look very similar. Differences in which atoms are where. And if we can do this with that guy, we can do the same thing with this guy over here. And triple bond NO. Now here's a question. Are these resonance structures? Do they just differ in placement of electrons? No. They differ in how the atoms are connected, right? These two are resonance structures, and these two are resonance structures. So now we're going to look at formal charges. Any questions about how to draw those guys?
Why did you draw the ones under the triple bonds? Why did you, I mean, the top was happy, right? So
The top was happy. Why did I mess with happy and do this? Because I can also make them happy doing it this way. And so I should try that and see what happens. The other example we had, there was only one double bond, and then we were like, well, why give it to that nitrogen? Why not give it to the other nitrogen? So here, this second bond here, why give it to this nitrogen and not give it to this one and give this one a triple bond? It's kind of the same idea. Yeah, it's like, yeah, but you got one that worked. Why mess with it? Well, because we'd like to mess with stuff. So let's see what happens with formal charges. So what we're going to do is we're going to mentally divorce these guys and see how many electrons they end up with compared to how many they came in with. Nitrogen has 5 valence electrons, right? Got it right that time? When we separate it out imaginarily, how many electrons does it have in this structure? 6. 5 minus 6 is what? -1. So that means the nitrogen has a formal charge of -1 in the structure. How many valence electrons does oxygen have? 6. In this, when we divide up the bonds, how many electrons does oxygen have? Somebody say it loud. 4. It gets this one and that one and this one and that one. Half of each bond. So 6 minus 4 is +2. And this nitrogen over here came in with 5, and it looks like he owns 6 in here. So he has a formal charge of -1. The formal charges on a neutral atom always add up to 0. If they don't, you did something wrong. So -1 plus 2 minus 1 adds up to 0. So that's a little check. Looking at the formal charges, is that a great Lewis structure? No. We'd like to see if we can get zeros. Well, let's look at what's going on down here. Excuse me. So nitrogen has 5 valence electrons. How many does this one own in this structure? 5. So 5 minus 5 is 0. I'll write these below. Oxygen has 6 valence electrons. How many does it own in this structure? 4. 6 minus 4 is +2. Nitrogen has 5 valence electrons. How many does it own in this structure? 7. 2, 4, 6, and this one, 7. Are you seeing how I'm getting the ownership? Is that making sense? Because if that doesn't make sense, the whole thing's a big old mess. So 5 minus 7 is -2. Well, we got a 0, but this isn't great either, right? So we're like, I don't really like either one of those. Let's try this other arrangement over here and see what happens. Oops. So here, nitrogen, 5 valence electrons. It owns how many? 6. So this is -1. 5 minus 6. Nitrogen in the middle. Brought in 5. Owns 4. 5 minus 4 +1. Oxygen. Brought in 6. Oxygen has 6 valence electrons. How many does it own here? 6. So this is 0. Okay, so those are already lower oxidation numbers than we saw for either of these guys, which is making both of these guys look really bad. Nitrogen had 5. How many does it have in this? It's got 5. So its its formal charge is 0. 5 minus 5 is 0. 5 valence electrons minus how many does it own? 4, right? 5 minus 4, that's +1. This oxygen, 6 minus 7 is -1. Any questions about the formal charges? Okay. So, looking at the formal charges, should we choose these guys over here or these guys over here? The ones on the right. So, we're just going to X these other guys out. That was a nice idea, but it didn't work out. So these are the resonance structures for N2O. And this is asking which resonance form is going to contribute more. Well, they both have +1, -1, and 0. So the magnitude of the formal charges is the same. Where would we prefer a negative formal charge to be? On the more electronegative element. Which is the more electronegative element? Oxygen. So in this structure, oxygen has the negative formal charge. Oxygen hogs the electrons. Oxygen is more attractive to electrons than nitrogen. And so this is more likely to be the case than this one. It is a combination of both of these, but this is like the dominant gene, and this is the recessive gene. Okay, so I'm Swedish, my husband's Japanese. Guess how many of my 6 children are blonde? 0. He has brown eyes, I have green eyes. How many of my kids have green eyes? 0. My children are brown, okay? Beautiful, beautiful brown. Brown eyes, brown skin, brown hair. Dark brown, but beautiful brown. Okay, my husband's genes have more influence on the outcome of my children than mine do. I just have like a whole bunch of recessive genes, right? So I had little influence on what my children look like. So this is my husband, and he's going to have more influence on the hybrid between these two than I am. Does that make sense? So we say that this guy, we need a different color. This resonance structure is going to contribute more to the correct structure. Now you had a question.
Yeah, I was just, because we have two elements the same, you know, we've got a triple bond, or like elements got a bond tendency to group together when they form an ion like this, even though the oxygen has more influence on it. Is there a tendency for like elements to group together when they form a bond with something else?
You mean, why is it N connected to N connected to O?
Yeah, I'm saying, is that a tendency?
At this level of chemistry, I would say actually not.
Okay.
Usually you would see something like oxygen in the middle. And looking at this, I just realized there's a third resonance structure that I didn't even think about. What else could we do with those two guys on the right? We could put the triple bond between the nitrogen and the oxygen. I mean, I didn't even think about that. So you're like, well, let's go with not thinking about that. No, we're going to think about it. So I'll draw him up here because I ran out of space. So what if we had nitrogen, single bond nitrogen, triple bond oxygen? Because we could make everybody happy that way too, right? We could get octets anyway. We got to look at the formal charges. So on this nitrogen, what's the formal charge? -2. Number of valence electrons is 5, minus the number owned here, that he would get in the divorce settlement. He's going to get half of the shared property and all of his own stuff. So 5 minus 7 is 2. What's the formal charge on this nitrogen? +1. What's the formal charge on this oxygen? +1. Now, this is also a resonance structure with these guys. And I don't know where my brain was. Somewhere else. Looking at these formal charges, is this a good setup compared to these two guys? No. Just based on, this has a 2 and 2 1s, and these guys had just 1s and a 0. So lower numbers are good. Then when we had to choose between equally low numbers, we're going to put the -1 on the more electronegative element. And also what's going on here, here's the negative formal charge, and here's the more electronegative element. So this is really going to be bad. This is worse than this one down here. Any questions? It's going to take some practice. Let's do another one. Draw the Lewis structure, including resonance structures, for diazomethane, CH2N2. For each resonance structure, assign formal charges to all atoms that have formal charge. Okay. So we're just going to see what we can come up with. So we've got a carbon and 2 nitrogens and 2 hydrogens. The hydrogens have to be on the outside. They have 1 electron. They have to be on the outside. They can only make 1 bond. So let's not worry about hydrogen for a minute, and let's see how we could connect the carbons and the nitrogens. Well, we could put the carbon in the center and put a nitrogen on each side. And then we could attach the hydrogens somewhere. And if we look at our guidelines where we put the more electronegative element on the outside, would this be a good thing? The carbon in the middle and the nitrogens? Yeah, that would work. Okay, so that's a possibility. Where to put the hydrogens? Well, we could put the hydrogens on the carbon. I'm going to run out of space. Okay, I'm going to start over and make this smaller so I can have, because I'm going to be writing a bunch of things here. So carbon, nitrogen, nitrogen, with hydrogens on the carbon. Not much smaller, but it's a little bit. Where else could we put those hydrogens? We could put them on the nitrogens, 1 on each. Might be fun. Or we could put both hydrogens on 1 of the nitrogens. We could do that. It gets complicated really fast. Are there other ways that those 4 atoms could be arranged? Yeah, there are. We could put the nitrogens together. We could put nitrogen, nitrogen, carbon, and we could put the hydrogens on the carbon, and we could put the hydrogens on this nitrogen and leave these guys empty. We could put the hydrogens on the middle nitrogen. You can't. Right, because hydrogen cannot form 2 bonds. He's too small. So he has to be on the outside. I think these are all the possibilities for connecting. How many electrons are we dealing with here? We've got two nitrogens. It's 10, right? And 4 from the carbon and 2 from the hydrogens. Oh, I should be consistent. 2 times 1. So 10 and 4 and 2 is 16, I believe, right? So we've got 2, 4, 6, 8. 10, 12, 14, 16. Double bonds. How can we do it? We can't do it on this one, can we? We can't write a Lewis structure that obeys the octet rule. We'll find out in a little bit that you can violate the octet rule, but we don't know that yet. So, okay, that guy didn't work out. On to the next one. Well, let's go to this guy down here. 2, 4, 6, 8, 10, 12, 14, 16. Okay, now we can do something with multiple bonds, right? So let's take those guys and put them in here. So this nitrogen's happy, that carbon's happy, this nitrogen's not happy. Hydrogen is happy just to be included in the structure. It's got a single bond, he's holding on, and that's all, and so we never have to worry about hydrogen. So we could take this one and share it over here. Everybody happy there? Okay. Before we leave that guy, are there resonance structures possible for this? What if we put a triple bond here and a single bond there? Well, we'll have to move the lone pair around too. Can we do that? Yeah. And if we did that, we could also do the other with a triple bond over here. Isn't this fun? That was a rhetorical question. I know the answer. You're saying, no, this is not fun. These are resonance structures of each other. The atoms are connected in the same way. Here we have two double bonds, and here, instead of putting this double bond here, we put it over there, made it a triple bond. And here, we made the triple bond on the other side. So, we don't know which one of those. We're not going to look at formal charges yet. Okay, let's try some of the rest of these guys. Let's do this guy. 2, 4, 6, 8, 10, 12, 14, 16. Not everybody being happy, so we'll take a lone pair from carbon and make a bond there. That nitrogen on the end is still not happy, so I'm going to take this other lone pair and stick it over there. Is everybody happy? Yes. Could I put the double bond over here? If I moved the lone pair, I could. Darn, too many possibilities. Okay, so nitrogen, carbon, we'll put a double bond there, H, H, and lone pair, and let's see, we need another bond here, and lone pair. No. Yeah. Two, 4, 6, 8, 10, 12, 14, 16, right number of electrons. Nitrogen has 8, carbon has 8, nitrogen has 8, hydrogens are good. Could we move the triple bond over here? No. Because of these two bonds with hydrogen, we can't do that. So, hallelujah, those are the only two possible resonance structures for those guys. This is getting messy. So this is a group right there. And these guys are a group. How about this one? So 2, 4, 6, 8, 10, 12, 14, 16. Well, let's take this lone pair and put it in here. And that's not quite enough, so let's take this lone pair and stick it in there. Is that happy? Sure, that's happy. Bless you. Are there resonance structures for that? Yeah, there are. Okay, so let's do this. Let's erase this guy. We crossed him off. We're done with him. And just give ourselves a little space. So nitrogen, nitrogen, carbon, hydrogen, hydrogen. Instead of triple bond, double bond, triple bond, single bond, what if we made both of those double bonds? So this carbon has 2, 4, 6, 8, the nitrogen has 2, 4, 6, 8, and then the lone pairs would be over here. So counting 2, 4, 6, 8, 10, 12, 14, 16. So that is in resonance with this guy. Let's look at the one on the top. We've got 2, 4, 6, 8 from the bonds. 10, 12, 14, 16. Can we put a double bond anywhere? But if we put a double bond nitrogen to nitrogen, then this nitrogen is going to have 10. And we can't do nitrogen to carbon because then this guy's going to have 10. So there's nowhere to put a double bond. So that guy doesn't work either. Phew, right? Because we didn't want to draw any more resonance structures. What about the guy on the bottom here? Well, let's see. 2, 4, 6, 8, 10, 12, 14, 16. Well, we could take this one and stick it over here. And then, well, I shouldn't have taken that one. I should have taken this one and put that back over there. 2, 4, 6, 8, 10, 12, 14, 16, 18. What? 2, 4, 6, 8, 10, 12, 14, 16, 18. Oh, I got too many electrons. So that's not quite right yet. So we need to take this guy and make it a triple bond. Does that work? That works. Yeah, we could also, instead of a single and a triple, we could do 2 doubles, right? So we'll squeeze that in here somewhere. H, N, H, N, C. 2, 4, 6, 8, 10, 12, 14. Am I counting wrong? Oh, on the carbon. There's no place to put those. That's not right. So we'll do a curvy double-headed arrow for him, and maybe we'll draw a purple box around him, just because we got to keep these guys separate. We have way too many possibilities, don't we? Way too many. But we'll get lots of practice with our formal charges. Okay, let's start over here. This nitrogen, what is the formal charge? 0. Nitrogen has 5 valence electrons in this structure. It's got the 2 lone pairs and half of the bonds, which is 5. What's the formal charge on the carbon? 0. What's the formal charge on this nitrogen? 0. The hydrogens are always going to be 0, so we can ignore them. So is that a good Lewis structure? Yeah. It's like, could we just stop now? Would that be good enough? Oh, we got to go check out the others. This guy. Formal charge? -1. So 5, the number of valence electrons, minus 2, 4, 5, and 6. 5 minus 6 is 1. Negative. And the carbon here? 0. And the nitrogen? +1. So that one's not as good. But we'll leave that combination on the table for consideration. Let's go do this guy over here. Formal charge for the nitrogen on the end, -1. And the guy next to it, +1. And the carbon, 0. Okay. Is anybody not quite seeing how I'm doing the formal charges? Because now's the time for a little more explanation. Okay. Formal charge on this nitrogen. What is it? 0. And on this nitrogen? +1. And on this carbon? -1. Okay. So comparing this pair of resonance structures to this pair, which one wins? This first one wins, right? Because this guy had a 0. So we're going to take those off the table. Not because they're impossible, but because there's a better option. This guy down here, this nitrogen. Formal charge is what? This one right here. 0. And this nitrogen? +1. And the carbon? -1. Okay, so how about this nitrogen? +1. I'm just going to write right on top of him. And this one? Also +1. And that carbon? -2. So in the purple box there, is that a good set of resonance structures? No, that stinks. That's like worse than the second one. Okay, these guys over here. This nitrogen. +1. And this carbon, 0. And this nitrogen, -1. This nitrogen, 0. The carbon, 0. And this nitrogen, 0. Ooh, writing in the wrong place, 0. Uh-oh, we got another 000. Darn it. This nitrogen, -1. This carbon, this nitrogen, +1. Now, did they ask us to choose the best ones? No, they didn't. I think that both of these exist. But the exercise here is doing formal charges. We can see that these, this one and this one, in terms of formal charges, are pretty comparable. Here we've got the same low numbers, 1s and 0s. Here we've got the +1 and the -1 are both on the nitrogens in these two and in this one, and so we can't really say, well, this one has the negative charge on them, or electronegative, and so that one's better. So it's pretty much a wash comparing those. But we got a lot of practice with the formal charges, right?
So if both of those exist, they're still the same molecule?
They're not the same molecule, actually. They're isomers. Get into organic chemistry, and because of the nature of carbon, you can get multiple combinations for the same molecular formula. And they have different properties and different names. Yes, different names. I believe, based on the name diazomethane, that the one they're talking about is this guy right here. Because of the diazo, it's meaning 2 azo groups on methane. Methane is 1 carbon, so there's 1 carbon, and we've got 2 NH groups. This one has an NH2 group on one side and an N on the other side, and so that would be named differently. But that's organic chemistry. We don't want to go there. Okay.